This is a lesson about magnetic forces on moving charges in a unit on magnetism. This has many really cool applications, but I need to take several steps in order to build the concept over a couple of lessons. And before we move anywhere, there are a couple of key concepts and techniques that I need to show you to remind you about as we move into the 3D material. We're definitely moving into the realm of 3D and having representations and understanding how the vectors work in 3D is going to be crucial for really understanding this material. So the first thing I wanted to remind you of was representing in 3D. Along the plane of the presenting medium, it's really easy to put an XY plane and represent up and down and left and right. But we're going to need to represent in and out. And that's done with an arrow. Of course, all vectors are arrows. So if I think about an arrow moving away from me into a page, I will see its fletchings at the end. And if I think about the arrow moving towards me, I will see the tip of the arrow coming out of the page. And so these are the two representations that we use for into the page and out of the page, and we will be using these as we move along. Additionally, we will have some 3D representations to better help visualize the 3D aspects of different situations. So be prepared to interpret 3D sketches and also draw 3D sketches. Another thing mathematically that we need to talk about is the cross product and how right-hand rule works. This is typically something taught in calculus class as you look at calculus on vectors. And the cross product is a measure of how perpendicular two vectors are when you multiply them together. There's also the dot product, which asks how parallel two vectors are. But here we're looking at how perpendicular they are. And now we're looking at a 3D matrix because the resulting vector points perpendicular to the plane of the original two vectors. Due to the vector nature of this, order matters. Due to the vector nature of a cross product, the order matters, and the direction is given by right-hand rule. So the example I picked over here, and to make it concrete, to have something to really anchor real life into these concepts with the cross product and the right-hand rule, is torque. This is something that we covered in the basics of classical mechanics, and you can look back at that video. But the big thing that we got here is it depends on the radius vector and the force vector, and this is a cross product. When we think about this force causing this plank or board or whatever to rotate, we can see that it's going to cause it to rotate in the clockwise manner. And what we would know is that then the force is applying a torque in the clockwise manner, but when we represent that, it's into the page. Okay, and that comes about by right-hand rule. I twist in the direction of that torque and I get my thumb into the page, and so that is the vector direction of torque. It's into the page. If the force didn't apply any torque, let's say I have this force downward, F2, it's not causing any torque, right? And so these two vectors, R and F, are parallel to one another, so I don't get any cross product out of it. The cross product would be 0 between R and F2, whereas it's non-zero for this force that is somewhat perpendicular, right? It has a perpendicular component to the radius. So we're looking at vectors, and when I do this cross product, we're going to get a torque into or out of the page, and in this situation, it's into the page. I do a cross product into the page, it rotates clockwise, and my thumb goes into the page when I rotate it in the clockwise manner. Okay. Let's get into the details of how to right-hand rule a little bit more. And let's remember that order is important. I have to do it in the order that is in the cross product. And the original, this is the proper way to do a right-hand rule. If you were in a math class with vectors, learning how to do a right-hand rule, it's to hold your hand flat and you have fingers. Your fingers will point in the direction of the first vector. So in the torque situation, the direction of the first vector, which is R, would be downward. Then it says rotate the palm towards the second vector. So if I'm looking at that picture there, R is downward. My palm would face towards the left. That's the direction of the force. And then it rotates, and I'm just going to follow that around. That's a clockwise rotation. And that's what you do. It's like you cross one vector into the other, and that's why they call it a cross product. You cross one vector, you cross it into the other vector. And the third vector is going to be the direction of your thumb, okay? So that's, to me, a proper right-hand rule. In a lot of textbooks, you see this called right-hand rule too. And to me, it's in a very intuitive way to do right-hand rule, because we saw in the beginning, I just curl my fingers right hand. So that's why I call it curly right-hand rule. I curl my fingers clockwise or counterclockwise, and my thumb gives the third dimension and the direction of that vector, okay? Right-hand rule 1 is typically the first right-hand rule taught with this material, and that's why they call it right-hand rule 1. And it's just a flat hand. You orient your hand, and notice your hand gives 3 directions, and they're all perpendicular to one another. They're all orthogonal. So a typical plane would maybe have an X along this axis and a Y along here. Notice the palm is outward. That would be the z-axis. So if you're thinking in terms of axes, just x, y, z, that's the easiest way to think about it, is x, y, and then your palm is z. There's 3 dimensions on your hand. And so you put your thumb in the direction of the first vector. So this is why it's a different right-hand rule, is because it's not fingers first. It's thumbs first. Thumb goes in the direction of the first vector, then your fingers in the direction of the second vector, and the third vector will be your palm. So that's how to use right-hand rule. It can be shorthanded like this. Notice that I just created 3 dimensions with these 3 different fingers. All right. So I still have X, Y, and then Z is the outward axis here. So 3 dimensions. And as you develop an understanding of how to use these right-hand rules, I've seen different people accommodate them differently, as long as how you use it is consistent for solving problems, and you get the right answer and are thinking about it in 3D in an accurate way. I don't care which version of these right-hand rules you use. A lot of people prefer this one. This is a very easy one, and this is the one I'm going to use. But right-hand rule 2 is also a very intuitive curly right-hand rule, like which direction is something moving in a circle, and then that the other vector will be pointing your thumb. So I will give examples of these as we move forward. The first thing we're going to look at is magnetic forces on moving charges. And what we're going to see is that any charge moving in a constant magnetic field, and we're going to let this be a constant magnetic field. All the applications that I've chosen and that we use this for, we choose a constant magnetic field. There's no integral calculus going on here. The constant magnetic field gives us this equation. The magnetic force equals the magnitude of the charge times its velocity crossed into the magnetic field. So we just looked at cross product. What does this mean? So when I look at the velocity, and note that there's the order, this is going to be the first vector, the velocity, and this is going to be the second vector, the magnetic field. And so right-hand rule 1, like I said, the thumb is the first vector, and you align your thumb along the velocity, and then it gets crossed into, and your fingers will be the magnetic field, okay? When you get those lined up, that third dimension created by your palm is going to be the direction of the force, okay? So here I would call the velocity to the right. The B field is going into the page, and the force is upward, okay? And if I drew that on here, here's the velocity to the right. The B field would be into the page, and I can represent it with an X, okay? That's that vector pointing away from me. So that's into the page, and the force, the magnetic force, is upward. And we can do that with right-hand rule, right? V to the right, B into the page, and force upward. So you can tell when I'm doing a right-hand rule, I'm looking at the page, and you may want to listen to my words and make your hands do what I'm saying, and then maybe check my picture, because it will be a mirror image of each other. We should be. So that's how to represent that in the plane without 3D. We assume in and out is that third dimension. This results only when the velocity and magnetic field are not parallel or anti-parallel to one another. Because we can see if they're parallel or anti-parallel to one another, there's no cross product. I know a lot of students want to do that if the velocity is in one direction and the B field was in the other. Remember, what a cross product asks is how perpendicular are two vectors, and these two vectors are not perpendicular to each other at all. You could technically cross that into that direction, but it's not really addressing the question of what a cross product asks is how perpendicular are these two vectors. So in this situation, they're zero. They're not perpendicular to each other at all. The last thing to remember is that the force will point perpendicularly away from the plane created by the other two vectors. All right, these first two vectors form a plane, and you can form that with the thumb and your fingers, whatever direction that is, and the force will always be perpendicular to that plane. So when you're doing your right-hand rules and figuring out directions, that can be some tips. Let's work on some examples here to see if you're getting the idea. So I picked 5 examples. And so we have to draw the situation. I described the vectors, and we have to draw the situation and then find the direction of the force. That's all this is. So if I have a velocity vector to the right, I'll put the velocity vector to the right, and I have the B field pointing upwards, so I can represent these in the plane of the screen. Okay. So I'm going to use right-hand rule. I have velocity pointing right and the B field pointing outward, and my palm is pointing towards me, right? That's how I'm putting this in the screen. When you do this with the screen in front of you, you have velocity to the right, B field up, and your palm is facing towards you. So what we're going to say is that the force is coming out of the page, and that's the direction of the force is out of the page, right? Towards you, towards us, which is out of the page. Okay, so that's what they would put there, is out of the page, and that's the drawing of a vector coming out of the page. Okay, so hopefully you're getting the idea here. I'm going to keep practicing just so to make sure that you're getting the idea. You can pause it maybe and see if you can do these, and then check your answers with mine as well. I'm going to keep moving forward. There's the velocity to the right, and now it says the magnetic field is into the page. So I get magnetic field into the page, B. And so I'm going to do velocity to the right, B field into the page. My fingers are going to point into the page, and I see my palm is pointing upward. So I'm going to draw the force on there, upward, F. And so I get an upward force there. So once you figure this out and you're getting consistent, it's just a matter of practice. So I'm going to keep moving forward. We're going to have a velocity out of the page. So there's the velocity out of the page. The magnetic field is pointing right. There's B. So I have thumb out of the page, B towards the right, and you can see that my palm is upward for this one. Okay, so I end up with a force upward here. And in all of these situations, note again that there's a 90-degree angle between the plane formed by the B field and the velocity vector and this force. That's a 90-degree. There's a 90-degree here as well. We can't really see it. Maybe if I go like this, the force coming out of the page, if I think this is in 3D, this would be a right angle here. They're all 90 degrees from one another. So velocity to the left and B field to the right. We're going to note in this situation that these are anti-parallel to one another, and so there's no perpendicular component, and so the force will equal 0 in this situation. Finally, we have the velocity into the page, so there's the velocity, and then the magnetic field is down, so then I'm going to go thumb into the page, away from me, and then B field down. And so I get my palm pointing to the left. Okay, so it goes like this. There's the force there. Before I leave this slide, I want to talk about one more thing, and that's what's to do if the charge is negative, right? So when I have charge, I have positive and negative charge. And what I did was I answered all of these questions as if it were positive. I didn't mention it until this point because I wanted you to get used to right-hand rule. So when we do right-hand rule, we're assuming it's for the positive charge. If the charge is negative, what we're going to do is reverse the outcome. So for instance, on this last problem that we just looked at, we decided that velocity was into the page, B is down, force is to the left. All right. Go that far, and then if your charge is negative, you just say, well, it's the opposite direction. So the force on a negative charge will be to the right instead of the left. Okay, so that's how we do that, and I'll have some examples of this as well. You'll be asked to do some of this for homework problems, I'm sure, and then also we're going to see applications of this, and it will be relevant in those situations. So you will be responsible for knowing how to use right-hand rule in different situations. Calculating the magnetic force, that's often a pretty easy thing to do. And this is not with the cross product. When you do a cross product, you end up having the magnitude of the first vector, the magnitude of the second vector, and sine of the angle between them. And so we have Q VB times sine theta. And notice that Q is the magnitude of the charge, and we're just doing the magnitude here. You can figure out the direction with right-hand rule and then just calculate the magnitude using this equation. So don't include the sign of the charge. I've already taken the sign of the charge into account when I figure out the direction of the force. So I only put the magnitude of the charge in there. There's the speed of the charge, this external constant magnetic field. It's uniform in this region. Whatever the magnetic field is, we assume that it's all in that region and it's completely uniform. And then theta is the angle between the velocity vector and the magnetic field vector. It's not just whatever angle you're given in the problem, so please beware of detractors or the information you're given in the problem, and you will want to draw a picture of these vectors when you do these problems. Right-hand rule for positive charges. For negative charges, do right-hand rule as if for positive charge, then flip your result 180 degrees. Now that we have the basics for how to find magnetic force, direction, and magnitude, let's look at an example. This is called Proton on Earth. I chose just an everyday example with a particle that we're familiar with on some level. It says at a certain location, the horizontal component of the Earth's magnetic field is 3.1 times 10 to the 5th Tesla due north. A proton moves with just the right speed for the magnetic force on it to balance its weight. Determine the proton's direction and speed. Okay, so I'm going to think about the magnetic field of the Earth here. Here's the Earth, and here's north. And so I'm going to have the magnetic field pointing north at some spot. It says due north. And the magnetic field, the magnitude is right there, 3.1 times 10 to the 5th. It says determine the proton's direction and speed. So if we want the magnetic force to balance its weight, let's draw a free body diagram of the proton. Here's the proton, and I know that the weight on a proton is downward, like here's the ground. Okay, so we're already looking at a 3D situation here where here I'm looking at the top, and the ground is a flat surface that I'm looking at. It hasn't really no dimension, but then I can look at it from the side. The magnetic force has to balance its weight, and in order for that to happen, the magnetic force must be upward. Okay, so those are the two forces we see they're balancing. Let's do this. Let's imagine looking at the proton from this direction, a side view, okay? So I'm going to take this picture and flip it so that the ground is on the side, and then the magnetic field here from the Earth is pointing in this direction. Okay, so this is north. And here's the ground. So you're getting this side view, you're getting it rotated in your head. And so then the question is, which direction does the proton have to be moving in order for the magnetic field to be right, the force to be up, and which direction is the velocity vector? Okay, so this is what I'm going to do. I know the B field has to be my fingers, and the force has to be my palm. I'm going to line my fingers to the right and my palm upward, all right? You've seen that, fingers to the right, palm upward, and I get that the proton, the velocity vector is coming at me. It's coming at me. So the velocity vector I'm going to put on here, V, has to be out of the page. And so it seems like in order for this proton, and I can do it over here as well, if the velocity vector is eastward and the B field is upward, so then when I line those out, my palm is out of the page, the force from the magnetic field is out of the page, and I know that would cancel gravity into the page towards the center of the Earth. So the direction that this proton is moving is east. It's moving eastward. So usually that's the harder part when you're first learning right-hand rule, is which direction, how do I line this all up, and what's going on. So that's how to do that. The speed, I think, isn't too bad. We know that the force upward has to equal the force downward, right? Newton's second law, the net force has to equal ma. And so the net force, I have the magnetic force upward minus the weight downward, and that equals 0. There's no acceleration up or down. It's just traveling a constant velocity along there. Those two forces balance each other. So the magnetic force is QVB, and we're going to note that the angle between the B field and the velocity vector, the angle is going to be 90 degrees. So we get sine 90, and that has to equal mg. I'm solving for the speed, so I'll solve for v in here. V equals mg divided by qb sine 90, but I'm going to note that sine 90 is 1. Just put that in there for you. So these are all quantities that are constants that we know. The mass of a proton, 1.6726 times 10 to the negative 27th. Okay, so there's the mass of a proton. Gravity, we know, near the surface of the Earth, we can just put 9.81. The charge of a proton, we know the charge of the proton, 1.6 times 10 to the negative 19th. And they also tell us the magnitude of the magnetic field at the surface of the Earth there, 3.1 times 10 to the negative 5th. So when you run all of those through your calculator, we get the velocity of this proton is 3.3081 times 10 to the negative 3rd meters per second. Or when you look at that, that's about 3.3 millimeters per second. And I can move that fast, 3 millimeters per second. I'm probably doing it right now. So we can see a singly charged ion can experience a force equal to its weight near the surface of the planet at reasonable speed, at a very realistic speed.